In this video, we're going to learn about the structure and properties of different kinds of solids. So ionic solids, molecular crystals, giant covalent compounds, and even the allotropes of carbon. So first of all, ionic compounds, if you recall, involve the bonding between a metal and a nonmetal, and they get arranged in a 3D crystal lattice structure. And that structure is explained by the arrangement of the positive and negative. So these are the positive, these are the negative ions. And they're held together by electrostatic attraction. So we call those ionic bonds, but those bonds are explained by electrostatic attraction, the negative ions being attracted to the positive ions and holding each other together. So some of the forces involved in this type of bonding are ionic bonds, first of all, like we just talked about, but then also London forces or van der Waals forces. So remember, those are the weak forces of attraction between the positive nuclei and the negative electrons of surrounding atoms and molecules. Some of the properties of ionic solids would be that they're hard and brittle solids, so they're hard to crush their crystals. They conduct electricity when they're in liquid state, so if they've been either liquefied, melted, or dissolved in an aqueous solution in water. They have high melting points, and then their forces are stronger than intermolecular forces because these are intramolecular forces. Some examples of ionic solids would be salts, so sodium chloride in the example we already talked about, calcium carbonate, magnesium oxide, and so on. So metallic crystals are when positive metal ions are arranged with delocalized valence electrons. So we talked about this in another lesson. Remember that when metals bond together, they release some of their valence electrons and they're free to move around through the solid. So that makes the metal ions positive because they've delocalized some of their electrons, and then the electrons are negative, floating about. So the bonding of metals is then a result of attraction between the delocalized valence electrons and then the cations, the metal ions. So the forces of attraction here are the metallic bonds. The properties of metallic solids are, they can be either hard or soft or even liquid. If you think about mercury, and then the alkali metals are quite soft, and then other metals are quite hard. They're excellent conductors. Metals are malleable and ductile. These are all properties we already know about metals. The melting points decrease as the size of the cation increases. So the positive ion, if it's a large ion, then the melting point will be lower. Some examples of metals would be copper, tungsten, sodium, and so on. Our next type are molecular crystals. So these crystals contain recognizable molecules within their structures. So this is an example of water all bonding together with one another. A molecular crystal is held together by intermolecular forces. So these types of molecules, they'll be held together, the molecules themselves, by their covalent bonds. There'll be London forces. There'll be dipole-dipole interactions if they're polar. There'll be hydrogen bonding if those dipole-dipole interactions are between hydrogen and then one of the electronegative, like fluorine, oxygen, etc. Their properties are that they're relatively soft, and they also have relatively low melting points. They cannot conduct electricity. And some examples would be rock candy, the crystalline form of table sugar or sucrose. That's an example of a molecular crystal. They form crystals that look like ionic crystals, but they're actually molecular. So when you dissolve them in water, they would not be conductive. Our next form of bonding would be giant covalent structures. So a covalent crystal has true covalent bonds between all of the atoms in the crystal. So these would be nonpolar molecules. And you can think of a covalent crystal as one giant molecule. So this is an example of silicon dioxide. So it's hard to kind of tell where one molecule starts and the next because they actually are forming covalent bonds between each of the molecules instead of having hydrogen or dipole interactions. And this is a closer up look of that too. So the force of bonding in this type of compound are covalent bonds. So they're very hard and brittle, so they don't bend. They have very high melting points because of that very strong overall bonding, because instead of using intermolecular forces to hold them together, they're actually bonding with each other covalently. They're insoluble, they won't dissolve in water, and they're non-conductors. So some examples would be diamond or amethyst, silicon dioxide. So now we'll talk about some of the allotropes of carbon. We've mentioned before in other lessons that carbon is a very special element because it is so versatile in its bonding. Because it has 4 valence electrons, it can bond with 4 other atoms. So it can bond with itself as well. So it can bond to form a variety of pure carbon structures like diamond, graphite, and the fullerenes. And each allotrope will have different properties. We're going to discuss each of those now. So the first one's diamond. Diamond, you probably know some of those properties already. You may have heard that diamond is the strongest molecule on Earth, and you may have heard that nothing can cut a diamond but another diamond or a laser. So diamond is a giant covalent structure, and every single carbon is covalently bonded to 4 others, and they have bond angles of 109.5 degrees. And these strong bonds make diamond very hard, and they have a high melting point and a high boiling point, and they're poor electrical conductors. So if you take a look, so this carbon, if you look at the 4 that are attached to it, that looks like a tetrahedral shape, and that's what explains these 109.5 degree angles, because tetrahedrals also have the same bonding. So again, very strong and very hard. In graphite, each carbon is bonded to 3 others, and then there'll be at the outsides lone little sticks where they're waiting to bond with something. So these form sheets that layer on top of one another, and each carbon has a delocalized electron, which explains graphite's conductivity. It's very soft, and that's one of the reasons why we use graphite as our pencil leads. No lead is involved in pencil leads. They also have a very high melting point, graphite, and if you take a look here, you can see that these layers, these single layers, layer on top of each other like so, and then they're being held together with bonding. So fullerene, or C60, this molecule is really interesting, or this allotrope's really interesting. We have 26 carbon rings, so there's one of them, and 12 5-carbon rings, so there's another one. And every carbon is covalently bonded to 3 others, just like in graphite. And each carbon has a delocalized electron. But in this case, because of these ring structures, the electrons can't jump from one ring to another, so it's not as good a conductor as graphite. So that's fullerene. We sometimes call this Buckminster fullerene, named after an architect named Buckminster Fuller, who created these geodesic dome structures, buildings, and these are very reminiscent of those. They're also kind of reminiscent of a soccer ball. Now, graphene is like graphite, but instead it's a single layer of graphite. And when you're writing on your paper, you could actually be laying down a layer of graphene. And these atoms have a bond angle of 120 degrees between the atoms. So you can see there's one bonded to 3 others. So this shape is a trigonal planar shape. The same thing would be in graphite as well. So in between each of these, it looks like a trigonal planar. These molecules, or these allotropes, have a high tensile strength. They have high electrical and high heat conductivity. They're actually the most chemically reactive of all the allotropes. And the high tensile strength, a sheet of graphene has the tensile strength of 1,000 times higher than steel. So graphene is very, very strong, and their high electrical and heat conductivity could have some applications in, for instance, circuit boards. So graphene is quite an interesting allotrope, and it's one that's being explored for some handy uses in the future.